Hi, welcome to Machine Learning from Data. This is lecture 5, video 1. And in this video, we are essentially talking about training versus testing. The major areas that we'll be covering are summarizing the two questions of learning and then talk a little bit about theory of generalization. In fact, not just a little bit, but try to understand how the theory of generalization needs to adapt given the more practical side of things, and then come up with an effective number of hypotheses. So basically, does what we said in the previous lecture still hold or not? Okay, so without wasting any time, let's quickly check what we did in the previous lecture. So remember when we talked about the feasibility of learning, so when we were talking about the feasibility and eventually we came up with the answer that yes, learning is feasible, there were two major questions that we wanted to answer. The first one was, can we make sure that E out, which is the out of sample error, and the in sample error, are they close enough? Or can they be as close to each other as possible for some hypothesis G? And the answer to that question came out of something that's known as the Hofding's bound. So the first question is usually answered by the Hofding's bound, which gave us this equation. Right, so we got this equation, and within this equation we came up with the idea that this E in, and there is a relationship essentially between these three terms, and E out essentially depends on the value of E in and the generalization error, or also that's also known as the error bar. The important thing here, if you remember on the right hand side, was this graph was that there is a trade-off when picking the number of hypotheses. So it's because this error bar has the number of hypotheses as one of the important elements or one of the important variables, and as we increase this, right, this has an impact on E in as well as itself. So with E in, we saw that E in goes down as the number of hypotheses increases because we have a greater chance of getting a better hypothesis G, right? So this in sample error keeps going down, but the model complexity, which is this term itself, the generalization error bar, it contributes to the model complexity. If you remember, we said let's denote it by omega, and is a function of h and n, right? So this keeps increasing as we increase the size of the hypothesis set. And eventually there is this optimal value. There is some optimal value that exists because we can add these two, and that's what E out is essentially. Okay, so think about E in as something that came out of the sample that we have. So that's more like a training set, and E out is more of the testing set. And the analogy here is like you have a practice exam where you try to practice, but it's not quite the actual thing. And then your real knowledge is tested when you appear for the real exam, right? So that's the analogy that kind of helps us understand the relationship between E in and E out. Okay, so having said that, we are really interested now in this lecture to understand, we're to really get at what this generalization bound really achieves. What is this theory of generalization, and does it achieve what we want it to achieve, or do we want to make some adjustment? Or should this equation be used as it is throughout, or do we need some extra information? So that's what we're looking at. Okay, so this is my Hofding's bound or the generalization bound, right? Now, if we look at the error bar, so again, this term is my error bar, just to make sure, right? It depends on h, right? As I said in the previous slide. Now, what happens if h is infinite? What happens if h becomes infinite? Now, if this becomes infinite, then this error bar is almost meaningless because the bound also goes to infinity. Now, if you think about all the machine learning models, all useful models in machine learning have infinite h. So that kind of tells me that this bound is basically useless for all useful models, because even including the perceptron, if you think about the perceptron, it has an infinite number of hypotheses, right? Now, to study generalization in these models, we need to come up with a counterpart to this equation, right? Which most likely is going to be this equation, and we're going to see how we come up with this one, such that it deals with an infinite hypothesis set. Because as I said, most models are going to have an infinite hypothesis set, right? Most models will have that. And obviously, I cannot deal with it here because there is no meaning to that bound anymore, right? So what I want to do is I want to come up with eventually this equation, and a high level idea of this equation is that it will take care of the fact that despite having an infinite number of hypotheses, this error bar will still make some sense. So basically what I'm trying to say is that this theory will still hold, the theory of generalization. That's what we want. Okay. So in order to arrive at this, we need to go back a little bit and understand how we derived our H and how we came up with this. Okay, so going back, meaning of the cardinality of H, essentially we are looking at this. Okay, now if you remember how we came up with this, right, how we started with this, we said that the disjunction of all bad events will be guaranteed to have this. Let me remember, the G is the hypothesis that we finally select, right? And E out of G will be greater than my tolerance. And what we said is that of all those bad events, this must be there because my G will eventually be a part of my H, right? Now, if we think about it, we actually overestimated the probability using the union bound. Because let's say B sub M is a bad event. Right, let's say this is my bad event. This is how I'm denoting my bad events with B's, right? And that means that this quantity, which is E in HM, because M is, I'm talking about the event in terms of M, so it's the mth term in that entire thing, out HM, right? Greater than epsilon, this term, this entire thing. Let's say this is a bad event, and then what we said was we do not know which G is there, right? So we will use a worst case union bound. If you remember, we don't know which G, so there's probably one G, and so what we said was the probability of that one G, the probability of that event happening is less than or equal to the probability of any of these, right? BMs. Any of these, right? Which obviously is less than the sum of all, like the probability of all BMs. And M is from 1 to the cardinality of H. Right? Initially it was M, but then we said that let's denote it by H. So now this is what we said. Now, let's look at this like picture here. And before like even looking at the picture, if you just like think about this expression here, now if all these events, they are strongly overlapping, then the union bound is very loose, right? This is what's shown in the picture here on the left hand side. So from the picture, areas covered by each hypothesis correspond to its probability. So B1, B2, B3, these are like the event sets of outcomes, and obviously they can overlap, right? Now, according to the union bound, which we used in order to arrive at our final result, right? According to the union bound, the total area covered, what it meant was that the total area covered by B1, B2, or B3, like these, the total area covered by each of these is smaller than the sum of the individual areas. So that's what the union bound did, right? Now this is true, right? But this is a huge overestimate, especially when the areas overlap heavily. For example, in this case, like there is a heavy overlap. Essentially, everything might just like lie here, right? Much of the area is just like covered within the overlap. So we are just like simply getting getting a union of these events, although like there is a heavy overlap, right? So what it means is that many hypotheses will coincide, right? For example, think of the perceptron. We slowly vary the weights so that it's highly likely that many hypotheses will be very close to each other, right? A very infinitesimal, I would say, difference between many hypotheses. So what does this mean, all of this? This means, and I would like to highlight this line here, so there are effectively fewer than what I said, this term, there are fewer than the H, the cardinality of that, right? The number of hypotheses in the entire hypothesis set that are really effective, right? There are effectively fewer hypotheses than this h. So we need to replace that h by something smaller, right? Because we just realized that a lot of it is just like waste, right? So there has to be this effective number of hypotheses that should take place, or that should take the place of this cardinality of h. Because we just realized that this case can occur quite frequently. You can just think about the perceptron. This case might be happening multiple times, right? And we have to address that issue. Okay, so what do we mean by this effective number of hypotheses? Okay, so what we said here was that like many of the hypotheses might be similar, right? And if they're like really, really close, we need to measure the diversity or the difference in the hypotheses. Basically, we have to come up with some kind of a definition that will categorize these hypotheses within the hypothesis set. That okay, this is the measure, and based on that, if the measure of like a set of these hypotheses is this, then these are considered the same hypotheses. Otherwise, they are not. Some kind of like, because we saw that the similarity, and by the way, diversity is just the opposite of that. So we cannot go ahead with the similarity measure, because we can have infinite hypotheses and then we have no error bar, and then there's no meaning of that generalization bound, right? So somehow we have to come up with a measure of the diversity of H. Now, the mathematical theory of generalization is dependent on the fact that we should be able to account for that hypothesis overlap, that we just saw. So basically, we should be able to replace this H by something that is more effective, right? And less than this H, even when this H is infinite. Right, so obviously one idea is that we cannot directly use this h, right? Because this is going to be infinite in most of the models, right? So basically we need to measure diversity, the difference in the hypotheses. One idea could be fix any set of n data points. If h is diverse, it should be able to implement all functions on these endpoints. Okay, what does that mean, right? A very, very simple example could be something like this, and I'm going to like draw a picture. So let's say that this is my space, my input space, right? And what we're trying to achieve is we are trying to do a categorization of some data that we have. So basically we want a binary output, a +1 or a -1. And this is what the data looks like. Okay, let me first draw some data, and let me change the color. Okay, let's say this is what this is what I have, and my hypothesis that I have on this data is something like this. So this, maybe I could have come up with a better one, but that's fine. Basically, the point that I'm trying to make here is that these are all the hypotheses that I have, right? And if you look at them, like in terms of how good these are, and this is like, by the way, +1 and -1, let's say. Okay, so if we look at these, right, what are we trying to achieve? We are trying to categorize a +1 and a -1 for each of these data points. And all these are my hypotheses, right? So these are my hypotheses, and all of them, right, individually are actually categorizing the data correctly, right? But I have all those hypotheses, and their number will be counted when I'm doing the theory of generalization. So essentially, like having all of them in my H seems irrelevant, right? Because actually this entire set of like whatever the number of these hypotheses is this is actually one hypothesis, right? So I can just like come up with a single hypothesis that takes care of all of these, because eventually it all depends on what I want out of my data, right? And this is my sample. So basically all of them are pointing to the same result. I don't care which one I pick, or maybe I come up with something that incorporates everything, or maybe I come up with just one of them, because one of them just represents everything. It doesn't, although like these are different lines if you think about them as lines themselves. But that's not the point. The point is whether I'm getting a good classifier or not. And of course I am if I just pick one of them. So that's the fundamental idea that we're trying to get at. And in the next video, we'll discuss a way to quantify this idea that's known as the growth function. So we'll try to do that in the next video. So let's stop this one.